In this lesson, we're going to cover everything you need to know as an undergraduate about E1 versus E2 reactions. We'll talk about what's behind Zaytsev's rule. We'll talk about when we don't follow Zaytsev's rule, we do what's called Hofmann elimination or anti-Zaitsev elimination. We'll talk about the stereochemical requirements like Antiperiplanar for E2 reactions. We'll talk about how to distinguish between the two, and we'll definitely work several examples at the end of this lesson. And if you'd like to be notified when I make more of these lessons, just hit the subscribe button, or not. I will not be offended. In fact, I'll never know. And if you're looking for practice problems, check out chadsprep.com. I've got two premium prep courses, my standard one, as well as one specifically designed as a refresher course for the ACS standardized final. All right, so let's have a little fun here. And before we can talk about elimination reactions, we really got to start this off by talking about the stability of alkenes. And it turns out how substituted an alkene is, it totally affects its stability. So the way we're going to look at this here, so it turns out the most substituted alkene, we're going to look at an alkene here, and each of your sp2 hybridized carbons is bonded to two other things for a total of 4 other things. And if all 4 of these are bonded to carbon chains, and I'll just make them methyl groups for ease, that's as stable as it can get. And it turns out the molecular orbitals forming these carbon-hydrogen bonds are going to overlap with the pi electrons in the alkene through what we call hyperconjugation, same thing that stabilizes carbocations. So, and that delocalization from that hyperconjugation actually makes the alkene more stable. And so the more of these carbons you're bonded to, so the more of that hyperconjugation you get, the more stable the alkene. So we would call this a tetrasubstituted alkene. And as we work our way up, I'm just going to replace one of these carbon chains with a hydrogen. So in this here is going to be a tri-substituted alkene, and with the hydrogen here, all we've got is an s orbital involved in the bonding, and there's no chance for this hyperconjugation. So again, it's all these carbon-hydrogen bonds that are actually involved in that hyperconjugation. So with none of those present, no chance for hyperconjugation, and so for a tri-substituted alkene, it's not quite as stable, and it's going to be higher in energy up the chain. So next on our way up the list are going to be di-substituted, and it turns out there's a couple of arrangements you should definitely be able to compare, and one is trans here. Cool, and the other here is going to be cis. Cool, now these are both di-substituted arrangements, but with a different geometry here, so double bonds can't rotate, so these are distinct from each other. So, and the trans experiences less sterics than the cis, where these two methyl groups are closer to each other, and as a result, the trans is more stable, lower energy. Cool, moving on from there, we'll then go to a monosubstituted alkene, where 3 out of the 4 positions are occupied by hydrogens and just 1 carbon chain. And then finally, we'll get a completely unsubstituted alkene. This would just simply be ethylene, and it is the highest energy here of our alkenes. So once again, to summarize, so the more substituted the alkene, so the lower the energy and the more stable. Okay, first we're going to take a look at the anatomy of an elimination reaction here. So in this case, an elimination reaction, they call it elimination because we are going to eliminate 2 sigma bonds to make 1 new pi bond. And we'll do it from adjacent atoms here. And just like you saw with SN1 and SN2 reactions, one of the 2 things we're going to lose here is a leaving group. And it's same leaving groups we saw with those substitution reactions. So halides are pretty common. And in this case, the atom losing the leaving group is often labeled again as your alpha carbon. So alpha carbon for where a functional group, in this case the alkyl halide, is located. So, and what we'll do is typically lose a hydrogen from one of the adjacent carbons. And so we've got a couple of options in this case. 2 different possible beta carbons. And so sometimes because you're going to lose a hydrogen from a beta carbon and then the leaving group from the alpha carbon, sometimes they even call this beta elimination. So, but in this case, elimination, we're going to lose 2 sigma bonds and make 1 new pi bond. So in this case, we're definitely always going to lose the leaving group. So, and then maybe we lose one of these 2 hydrogens to make one of these 2 products, or maybe we lose one of these 3 hydrogens to make the product on the far right. And what determines which we form as the major product is what's called Zaytsev's rule. So let's put that up on the board here. So we got Mr. Saytzeff, and when this guy emigrated over, so his name got transliterated in English a couple of different ways. So you might see it either way. And so typically we'll talk about Zaytsev's or Saytzev's rule, and this just helps us figure out when you got a multitude of elimination products, so which is major and which is minor. So what Zaitsev ultimately said is that when you've got multiple beta carbons, you always want to prefer the one with the fewest hydrogens. That's what his rule actually said. That's the way he worded it. So in this case, we can see that this beta carbon has only 2 hydrogens, and this one here has 3 hydrogens. So he would say prefer the one on the right here. Now, if we look at what's really behind this, the idea is that it's not that this has the fewest hydrogens, it's that it has the most carbons is often how we'd look at it. It is the more substituted carbon, and being the more substituted of these 2 beta carbons, it will form a more substituted alkene. And as we just learned, the more substituted alkene is the more stable alkene. So this is really what's governing Zaitsev's rule. So if we choose this beta carbon on the right, turns out there's 2 different alkene products we can get, one trans and one cis, and the trans being more stable. So this is going to be our major product. So this would be one of the minor products. So, and then this guy over here we'll learn is also one of the minor products. So to get the product on the far right, now we'd actually be deprotonating opposite of what Mr. Zaitsev says. And so Mr. Zaitsev's rule here is not about the only product you form, it's just about the major product you form. So preferentially take from the more substituted carbon, deprotonate there. So in this case, if we deprotonate on that less substituted side, we'll get this minor product. So, and get a couple of different names it might be referred to, and one of them is anti-Zaitsev, or again, as you prefer, anti-Zaitsev. So, but often much more commonly, so you'll hear it called Hofmann elimination when you form the least substituted alkene. Now, in this case, it's just the minor product. So we might call this the anti-Zaitsev product or the Hofmann product, kind of sort of. But we'll see in certain E2 elimination reactions, we can actually make the Hofmann product the preferred product. So, but most of the time, the Zaitsev's rule is going to allow us to predict the major alkene product in most elimination reactions. So we'll start with talking about E2 reactions, and in this case we call this elimination bimolecular. So we call it bimolecular because there's going to be 2 reactant molecules involved in the rate determining step, just like there was in SN2. So, and in this case, contrast with SN2, instead of having a nucleophile and a substrate, we're going to have a base and the substrate. And again, find your leaving group and you've found your substrate. So in this case, we've got our substrate. Is our alkyl halide. So, and sodium hydroxide, you should definitely recall from Gen Chem as being a strong base. So, and just like SN2 typically involved a strong nucleophile, E2 is going to involve a strong base. So, and definitely sodium hydroxide qualifies here. In this case, we definitely have an ionic compound here. So what you'll find is that there are several strong bases out there, but most of the strong bases we'll see in this chapter are going to have a negative charge on oxygen. Again, there are other strong bases that exist, but most of the ones you'll talk about in the context of elimination reactions that are strong will have a negative on an oxygen. All right, way this is going to work is we're going to have sodium hydroxide come over here, and he's going to deprotonate a beta hydrogen. So that's going to free up these electrons. Hydrogen can only have 1 bond, so if we're making a new one here, the old one breaks, and that's where the electrons come from to make the pi bond. And so that we don't violate the octet rule, this bond to bromine has to simultaneously break. So we are doing a proton transfer here, deprotonating. We are forming a pi bond, and we have the leaving group leaving, and these all happen simultaneously. So in happening simultaneously, just like in SN2, we call this a concerted mechanism. Cool, so all happens in a single step, just like SN2 typically happens in a single step. And we can take a look at our rate law here. So we see that the base is involved in this step. So, and we see that our substrate is involved in this step as well. And so in this case, first order with respect to the base, first order with respect to the substrate, second order overall adding those 2 individual reactant orders together. So if you double the concentration of the base, you'll double the rate of the reaction. If you double the concentration of the substrate, you will double the rate of the reaction as well. So the rate is proportional to each of them independently here. So we take a look, and if we kind of take a look at our specific reaction, so the base is sodium hydroxide. You could just put hydroxide here. So, and then our substrate is 2-bromobutane here. And so there's our specific rate law for this E2 elimination. Okay, so it turns out the E2 elimination here has some stereochemical requirements we need to address as well. So, and I've kind of drawn it just such a way. There's actually two hydrogens on this beta carbon right here. One that's a wedge and one that's a dash. And I made sure to draw the dashed one on purpose. And so if you kind of take a look at a relationship here, so this hydrogen is pointing down and is a dash. So in fact, let's put it right here, down and a dash, whereas the bromine is pointing up and is a wedge. And if you kind of look at where they are relative to each other, they're pointing 180 degrees apart. And it turns out they have to point 180 degrees apart. So, and when they do, we refer to that as being, technically it means anti-coplanar, but the word I'm going to write here is called antiperiplanar. And it turns out it doesn't have to be exactly 180. It has to just be really, really close to 180. So 180 degrees plus or minus a couple of degrees, kind of, sort of. And that's what anti-periplanar mean. It doesn't mean exactly 180, but it means really close to 180. Gives you a little leeway. So anti-coplanar is kind of the term I learned it with way back in the day. But anti-periplanar is kind of the more commonly accepted term now because it doesn't have to be exactly anti-coplanar, which again, anti-coplanar would be exactly 180 in the same plane but pointing opposite directions. But anti-periplanar means either exactly 180 or at least a little bit close. All right, so this is a stereochemical requirement of an E2 reaction. So now a lot of people don't like to draw it like this. They prefer, you know, let's rotate that around, you know, and let's get that bromine in the plane. And that way we could get another hydrogen in the plane, and they would actually rotate all the bonds so that we could put them both in the plane. And one, I agree. I mean, that's easier to see. We can see that the bromine points this way and the beta hydrogen points this way, and obviously I haven't drawn the rest of the molecule, and it's easy to see that, yeah, they point 180 degrees opposite and they're antiperiplanar. So, but you can see it here as well. So bromine here being a wedge and up, 180 degrees off, that opposite of that would be a dash and down. So cool. We can see that based on the reaction happening just as we've drawn it here, once we form that double bond, we're going to lock it into a certain conformation here. And I can see that these two methyl groups are trans to each other, and when the reaction happens, they get locked into that trans conformation. Now, on the other hand, we could actually rotate this around a little bit. So in this case, what I'm going to do is draw one more hydrogen in. So I'll draw this one in on red, and I'm going to rotate this bond around. So I'm going to move, and let's show this in green. Take advantage of all our colors here. What I'm going to do is move the methyl group to where that hydrogen is. The red hydrogen is going to go where the blue hydrogen is, and the blue one's going to go back to where the methyl is. So I'm going to rotate this single bond right here around in a circle to get the other hydrogen antiperiplanar to the bromine. You can see what that looks like. Cool, so in this case, the methyl group is now in the wedged position. So the red hydrogen is now in the dashed position, and then the blue hydrogen is now in the plane. So, and I've left that bromine right where he was. Cool, and now I can see that it's actually the red hydrogen that's antiperiplanar to the bromine. And so if the reaction happened in this conformation, I can now see that these two methyl groups wouldn't be 180 degrees apart anymore. And we can explain why we'd get the cis product forming as well. And so when you've got a beta carbon with two hydrogens attached, so assuming it's free to rotate, then you're going to get both the cis and the trans, the E and the Z, if it does have those stereoisomers, as it does in this case. Also, we could factor in that the other beta carbon over here has got three hydrogens, and at any given moment in time, one of those three is going to be in the antiperiplanar conformation. So, and in this case, this particular alkene does not have cis and trans, does not have E and Z possible. And you can kind of predict when that happens. When either side of an alkene has two identical things, there is no cis and trans. So typically you can turn cis into trans and trans into cis if you have either side and have the two groups trade places. And so if either side has two of exactly the same group, whether it be two hydrogens or two methyls or two ethyls, just two identical groups on one side of the alkene, there's no such thing as cis and trans, no such thing as E and Z. Cool. So we can see here our three products, and Mr. Zaitsev says, pick the top two. But we also know that trans is more stable than cis, and this is our major product, and these would be our minor products in this case following Mr. Zaitsev's rule. Cool, so that's the stereochemical requirement on E2 reactions. So, and this is kind of something pretty important in a couple cases, and we'll see a couple examples here where we see that importance. All right, a common type of question you'll see, really requiring you to distinguish, when this anti-periplanar hydrogen is present and when you've got to rotate a molecule to get there and stuff like that, is going to be demonstrated in this following couple examples. So in this case, we're going to predict the major product in these E2 reactions. I've got a nice strong base here. So we said our strong base is typically going to have a negative charge on oxygen. So in the last example, it was NaOH. In this case, it's going to be NaOCH3. So, and again, with metal and non-metal, that's definitely ionic. And got a negative charge on oxygen, that's a good strong base. Essentially comparable to hydroxide. All right, so in this case, I'm going to look at our alpha carbon in both cases, and then we'll identify our beta carbons. Now, the beta carbon on the left here does not have any hydrogens whatsoever, so we cannot form a double bond here. In fact, if we tried, we'd violate the octet rule for that carbon on the left. So no options there. So, but then we've got a beta carbon on the right. And with the beta carbon on the right, there's only one hydrogen present. And so in this case, that hydrogen is on the dash. And in this case, that hydrogen is on the wedge. Cool, and that's going to be important. In the top example, that actually already is anti-periplanar to the bromine. So the hydrogen and the bromine are 180 degrees apart. Again, a wedge and up versus a dash and down, that's 180 degrees difference. So we're ready to do this elimination reaction right now. Our base would come, deprotonate that hydrogen, we'd form the alkene, kick off the leaving group, and this would get locked in the conformation in which the reaction actually happens. And in this case, that means this is going to get locked in a trans conformation, or E, I guess is more proper, as we'll see. So, but these two benzenes are going to end up trans to each other just as they're trans to each other, so in the structure of the reactant when the reaction actually happens. Cool, so it turns out this would be the E isomer. So the major functional group on the left-hand side is the benzene on this side and the benzene on this side, and when they're the two higher priority, I shouldn't say functional groups, but substituents are trans to each other, that's E. Cool, and we don't observe the Z product in this reaction at all, so only the E. And the idea is that when your beta carbon only has one hydrogen, if E and Z exist for that compound, you're only going to get one of the two, because that hydrogen is only going to be anti-periplanar in one of the possible conformations, leading to only one of those products. So if we look at this next one here, there's a couple different ways to approach this, but this wedged hydrogen is not 180 degrees away from the bromine right now. It's just not. And so we're going to have to rotate this around before the reaction can actually happen. And so just like we did on the last example here, what we're going to do is we're going to move this hydrogen to where the methyl group is. We'll move the methyl group to where the benzene is, and we'll move the benzene to where the hydrogen is. We're going to rotate this bond right here between alpha and beta, in this case, 120 degrees, so until the hydrogen is anti-periplanar to that bromine right there. So let's rotate this around. All right, so in this case, the benzene is now in that wedged position. So our hydrogen now is in the anti-periplanar position to the bromine. So, and then finally this methyl group is now in the plane over here. And now this reaction's ready to go. And we can see that it's not the two benzenes that are going to be trans to each other, it's the benzene and a methyl group that are going to be trans to each other. And so our base again is going to come and deprotonate the anti-periplanar hydrogen, which frees up those electrons to form the alkene, causing also the leaving group to simultaneously leave. And so if we draw our product out now, so we see that we actually get the Z product. Now the two higher priority groups are on the same side, we say. So they're cis to each other. And so we get the Z product. Cool, and we only get the Z. We're not going to get the E in this case at all. So cool, we had to do some rotation and stuff like this here, but there is a little bit of a cheat here. What we could have done is said, if the reaction happens right now in this conformation, well then we get the E, just like we did above, right? So is it ready to happen? Well, it's not, because the hydrogen's not antiperiplanar. So then you're not going to get the E conformation. You'll get the Z instead. So I took the time to rotate the bond and show us, show the hydrogen and the bromine in the antiperiplanar conformation. But the truth is, if the reaction is ready to happen, great, like the one above. So where the H and the B are antiperiplanar, great. Then you know what the conformation is going to look like. So in this case, though, if the reaction is not going to happen, then you don't get the E. You get the opposite, in this case, the Z. If it happened in this conformation, we'd get E. Since it's not ready to happen, we'll get Z instead. So just a little trick, little shortcut. But again, big key here is if you only have one beta hydrogen, then if E and Z are possible, you only get one of the two, depending on the arrangement you've got. All right, in the next example here, we definitely want to cover cyclohexane because there's something special with cyclohexanes when it comes to antiperiplanar hydrogens and stuff. So first of all, I'm using a strong base here, so we'll know we're doing an E2 reaction. We'll find out that E1s use weak bases just like SN1 use weak nucleophiles. So in this case, got a negative charge on oxygen. In this case, it's sodium ethoxide, sometimes written as NaOET, but a nice, good, strong base that we commonly see when dealing with elimination reactions. So, and if we look here, our bromine here is on the alpha carbon, and in this case, we have got two beta carbons. And if we draw in their relevant hydrogens here, we got one here, and over on this one, we've got two hydrogens, one a wedge, and one a dash, and that's going to be important. Now, most single bonds are free to rotate, except when they're part of a ring. So a single bond that's part of a ring here, any one of these single bonds that's part of the ring, might have a little bit of rotation as possible, like when we're switching chair conformation stuff, but it just can't rotate freely like a single bond that's not part of a ring can. And that's important because if a hydrogen is not antiperiplanar, then it's never going to be. So, and that's important. And ultimately what that's going to mean here, and I'll just kind of give it away, is the hydrogen that's going to be antiperiplanar has to be trans to the leaving group. So if I look at bromine being on a wedge, to be trans, my beta hydrogen has to be a dash. That one's not going to work. That one's not going to work, but that one will. So out of our three beta hydrogens, only one of them is even possible. It's only one of them is possible to react in an E2 elimination reaction. So cool, Mr. Zaitsev would have said, hey, look down here. This beta carbon only has one hydrogen. This one has two. Use the beta carbon with fewer hydrogens, i.e. use the more substituted beta carbon. So, but we're not going to follow Mr. Hofmann's rule here. So when it comes to E2 reactions, this idea of having antiperiplanar hydrogen takes precedence. And this is one example where we'll find out that we'll do Hofmann elimination instead of Zaitsev elimination. All right, one thing we should do to kind of map this out is draw the chair conformation. Cool, and what I'm going to do, so bromine is a wedge, so I'm going to point that bromine straight up. So, and as we come over here, the methyl group is going to be straight down, and that hydrogen there is going to be equatorial over here. So, and then on the adjacent carbon, we've got a hydrogen pointing straight down, and then an equatorial one slanted off over here. And you can see that it's this hydrogen right here that'll kind of circle in red. That one points 180 degrees away from the bromine here. And so in this case, that's our antiperiplanar hydrogen. That's the one involved in the reaction. We can see that this hydrogen over here on the more substituted beta carbon, it's not antiperiplanar. If bromine points straight up, I needed it to point straight down where the methyl group was, but it doesn't point there. So that's why this hydrogen over here, it's not possible for it to react in this particular reaction. One other thing you should note is that when you've got a chair conformation, you typically have two chairs in equilibrium. So, and it turns out only when the leaving group is axial, and we'll find out that it and the hydrogen that's antiperiplanar will be transdiaxial, but only when the leaving group's axial is this reaction even possible. So in this case, we arrange this bromine is now going to be over here and be equatorial. So, and on the adjacent carbon, let's get that methyl in first. And draw in the relevant hydrogens. So, and here's that trans hydrogen here, but when they're equatorial, they don't point 180 degrees apart, and the reaction can't happen. And so we've got this equilibrium going. We need this conformation with the leaving group axial for the reaction to actually happen. Anything that hinders the formation of this particular chair conformation would slow this reaction down. So if I put a T-butyl group somewhere that forces it all to be in this conformation or mostly all in this conformation, you can actually shut down an E2 reaction completely. So, but the key is only one of the two chairs is actually going to be usable in an E2 elimination reaction here. All right, so if we go back to our product then, in this E2 elimination, so we'll form the double bond right there. So, and once again, we'll call this the Hofmann product. Or some people say anti-Zaitsev. Take your pick, but Hofmann's a little more, oh, and I can't spell apparently today either. So, because that is not how you spell Hofmann's name. It is a little bit of funky spelling though. One F, two N's at the end. So, and that's your Hofmann product. In this case, the Saytzeff product wasn't even possible. All right, so we've already seen one example where we might not actually preferentially follow Mr. Zaytsev's rule and do Hofmann elimination. So, and here I want to show the most common example of where you're actually going to do Hofmann elimination to get the major product. And it involves what we call a bulky base. So, and you can kind of see why they call this a bulky base. This is here potassium T-butoxide, and sodium or potassium T-butoxide is the most common bulky base. In fact, for many students, it's the only one they're ever presented with. So if we look at it here, the oxygen here, and again, this is ionic. So potassium's got a positive charge being a metal, oxygen being a non-metal's got a negative charge. And in this case, the negatively charged oxygen is bonded to a tertiary carbon. So, and that gives it some bulkiness associated with it. And as a result, it turns out it looks over at our beta carbons over here. We've got, in this case, our alpha carbons where the halogen again is bonded, and it's a tertiary carbon, which means there are 3 beta carbons, 2 that are secondary, and 1 that is primary. So let's give myself a little room here. And if we look here, the secondary ones each have 2 hydrogens, but the primary one out here have 3 hydrogens. And the idea is that our bulky base is like looking over here and saying, well, I got to deprotonate one of these beta carbons, but man, I'm big. And I'm just so big, you know, I just think I want to not get too close here because, you know, that would be a little uncomfortable. Let me just deprotonate the primary carbon. Cool, instead of the secondaries. And so it turns out he's, just due to his bulkiness, his sheer size, that's what he prefers to do typically. And as a result, we don't get the product we expect as the major product. We're going to disobey Zaytsev's rule here and form the double bond using the primary beta carbon. So rather than following Zaytsev's rule and using either one of these secondaries, it turns out due to symmetry, they're equivalent. So whether you form the alkene here or here, it's exactly the same thing. So we call the one on the left the Hofmann product, or the anti-Zaitsev product. And in this case, that's going to be the major product now. We'll call the one on the right still the Zaitsev product. But this time around, it's going to be the minor product. Now, sometimes, you know, somewhere down the line, we'll present you with something. We'll talk about the most stable product being the thermodynamic product. So, but in certain cases, you can actually have what's called the kinetic product be the major product, like we're doing here. So this is one example of that. We'll definitely teach you some further down the road when that's the case. But this is the kinetic product here, this Hofmann product. That's going to be the major when we use this bulky base. Now, it turns out that not every time you use a bulky base do you get the Hofmann product as the major product. But it's a little confusing to teach you when exactly you do and when you don't. So most of the time, most textbooks and most professors just kind of oversimplify this and they just say, anytime you use a bulky base, you're going to get the Hofmann product as the major product. So, well, in this case, the truth is this. So for those of you that might have been presented with the truth, if you use a tertiary halide, which I'll call a bulky halide, then yes, you're going to get the Hofmann product as the major product. But if you use a secondary halide, well, some secondaries that are bulkier still form the Hofmann as the major. But some secondary halides that are less bulky form the Zaytsev as the major, and it gets a little confusing, which is why for most of you, you're just going to be simply told to memorize that when you use a bulky base, the Hofmann product is the major product. The least substitute alkene is the major product. All right, I want to present to you one more example of where you might actually get the Hofmann product instead of the Zaitsev as the major product here. So in that case, it turns out when you have a bad leaving group, in fact, Hofmann actually got his name on the Hofmann elimination, which is properly a reaction of amines, for specifically a reaction involving a bad leaving group. Now, this wasn't the bad leaving group he dealt with, but it's the one we're going to deal with here in this chapter the most common one presented. Now, for many of you, you may never actually see fluorine as a leaving group. So, but if you do, fluorine is not a good leaving group. It is not a weak base like chloride, bromide, and iodide, or not a super, super weak base anyways. And being a little bit stronger base, he's not a good leaving group. And when you don't have a good leaving group, you often get the Hofmann product as the major product here as well. And so in this case, I still got a good strong base, and he's not a bulky base this time. We don't need the bulky base here. We just need a bad leaving group. That's another way to get the Hofmann as the preferred product. And in this case, once again, our major product is the less substituted alkene. And once again, this is a kinetic product. So it turns out, if we kind of take a look at what's going on here, that's not an O. Let's make it an H. So we're going to come and deprotonate that beta hydrogen. So, and that frees up these electrons to form the pi bond. And so we're like, okay, let's form that pi bond so that fluorine can leave. And fluorine's like, whoa, 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 slow down, guys. I suck at leaving. Let's just take this a little slower and let's back things up. So let's undo this. And yeah, hold up on those electrons. And this carbon's like, dude, hydrogen's gone already. You need to leave. And so we kind of get a little buildup of charge on that carbon. Now, this is not the proper mechanism. The proper mechanism, this still all happens in a concerted fashion. So, but it turns out in the transition state along the way, there is a buildup of charge on that carbon. And it is on the beta carbon specifically, and it's very anion-like. So we have a little bit of a carbanion-like transition state, and I'd rather have a carbanion on a less substituted carbon. So for carbocations, they're more stable with more substituted carbons, but carbanions are more stable with less substituted carbons, and that's why we chose to have this carbanion-like transition state on a primary carbon instead of on these secondary carbons. So we're still not forming the most stable product. This is still a kinetic product. So, but due to having a bad leaving group, little buildup of negative charge on that beta carbon. Again, if you're going to properly show the mechanism, though, it's still all a concerted mechanism. It still all happens in one step. But we just know that in the transition state, there is that buildup of negative charge on the beta carbon. Cool. So there's one other example of when we might do Hofmann elimination that you're not very likely to see, so I'm not going to take the time to cover it. But I do cover it on my website, chabsprep.com. All right, so now we're going to deal with E1 elimination reactions, and E1 stands for elimination unimolecular, and as you recall from SN1, this is a kinetics thing, and this deals with the fact that there's just one reactant molecule involved in the rate determining step. It has nothing to do with the number of steps. E1 reactions always have more than one step, but again, it's how many reactants are involved in the rate determining step. So just like SN2 and E2 were both concerted, E1 and SN1, neither one is concerted. They all happen in multiple steps. And what's nice is that for both E1 and SN1, they have the same rate determining step, both forming a carbocation. So if we look here, we're still going to do the same overall number of mechanistic steps, just not all at the same time. And so it turns out first step, your leaving group is going to leave. And so we're going to form a carbocation. And just like with SN1 reactions, because we're going to form a carbocation here, we are subject to rearrangements. Now, this one's not going to rearrange. It's secondary, and the two adjacent carbons, one's secondary, one's primary, wouldn't be a better location, a more stable location for a carbocation, so no favorable rearrangement here. So, but the leaving group's left. Now we have to deprotonate one of those beta carbons. So in this case, we've got hydrogens here on these two beta carbons. So, and what's nice, this is just always going to follow Zaytsev's rule, and we don't have to worry about anything involving antiperiplanar this or that, because the hydrogen that gets deprotonated and the bromine that leaves, they don't even leave in the same step, so there's no requirement about their relationship or anything like this. And so in this case, both these hydrogens are fair game, and all three of these hydrogens are fair game, and Mr. Zaytsev is king when it comes to E1 reactions. We're always going to follow Zaytsev's rule. All right, so it turns out water here is going to be our base. And just like in SN1 reactions, which typically involve weak nucleophiles, E1 reactions are going to involve weak bases, which generally have the same players as the weak nucleophiles, which will cause some problems later. But in this case, it's typically going to be water or alcohols. And so we're going to take and we'll deprotonate the more substituted beta carbon. So that frees up these electrons to form the pi bond, and we get our more substituted alkene. Cool, this will be our major product, our Saytzeff product. If I can spell, that would be great. Cool. Now there's nothing that says that this single bond can't rotate not being part of a ring, and so we form trans as the major. We'll also form some cis. Now it's still a more substitute alkene, so it's still technically a Zaitsev product, but not the major Zaitsev product. But also we could have deprotonated out here on the less substitute side, but that's going to be a minor product in this case. So our Hofmann product is minor. And this is pretty much how it works for all E1 reactions. E1, always going to follow Zaytsev's rule. Zaitsev is major, Hofmann is minor. For E2, it depended. Like we had bulky bases, and if you have an antiperiplanar hydrant or not, or if you have a bad leaving group. But for E1, always follow Zaytsev's rule. Now again, sometimes you got to worry about carbocation rearrangements, but you're always just going to simply follow Zaytsev's rule. It's nice. Cool, so we can see here that the first step, just like in SN1, this is our slow step or rate determining step, and the only reactant involved is our alkyl halide, our substrate. And so your rate law only has the substrate in it. The base is not involved at all. And specifically, if we wrote our specific rate law in this case, we'll have our 2-bromobutane in here. Cool, and so we see that the rate is first order with respect to 2-bromobutane, first order overall, since that's the only thing there. You double the concentration of 2-bromobutane, you would double the rate. And that's all there really is to say about our E1 reactions. So if you notice, there's a lot more nuances and special cases involving E2. E1, much easier to deal with. So, but you also notice that the slow step here is exactly the same as SN1. And that's one of the problems. So E1 and SN1 reactions almost always compete with each other. Almost always compete with each other. Okay, so since they're almost always competing with each other, we'll find out that you almost always get a mixture of products. One thing you can do, though, is that elimination reactions are favored at higher temperatures over their corresponding substitution reactions. And it's just an entropy thing. So just if we count up the number of reactant molecules versus product molecules, we'll find out that elimination is more entropically favorable than substitution. So, but outside of that, most of the time, if you're doing E1, you're doing SN1 at the same time, and you get mixtures of products. Later in the semester, we'll find out that that's a good reason why we almost always avoid SN1 and E1 for synthesis purposes. There are a few exceptions, but most of the time we'll just leave them out because they almost always get a mixture of products. And so if you're looking to get, just one product and a lot of it, E1, SN1 is not going to be a good way to accomplish that. And finally, just like we concluded the lesson with SN1 and SN2, we want to finish off by comparing E1 and E2, compare them in terms of substrate, base, solvent, leaving group, talk about some extra considerations so we can distinguish between the two. All right, what we'll find out is that E1 is pretty much exactly the same as SN1, whereas instead of we're talking about nucleophiles like we did in SN1 and SN2, we'll talk about bases though instead. And so E1 is all about the carbocation, just like SN1 is all about the carbocation, still forming in the rate determining step. And in this case, we want the most substituted carbocation possible, just like with SN1, and tertiary carbocations are the best, then secondary, and again, typically primary and methyls don't react in E1 elimination. So your base, it turns out, is not part of the rate determining step, and a weak base is okay. And again, most of your weak bases are going to be water and alcohols, who also qualified as being weak nucleophiles for SN1 reactions. So your solvent, just like, again, it's all about the carbocation, and to stabilize a carbocation, you have to have a polar protic solvent. But again, just like we saw with SN1, typically done in water and alcohols, not only are they the base, but they're going to be the solvent as well here, yet again. And then finally, the leaving group leaves in all these reactions, and so the same leaving group trend, in fact, this is the same for all of our substitutional elimination reactions we learned in these couple of chapters, and so we'll just kind of make it a big one here. So we saw that our sulfonate esters were the best, followed by iodide, bromide, chloride, and we saw how fluoride was a bad leaving group here as well. So this is true for both E2 and E1. Now if we contrast this here with E2, so we'll come back to the substrate in a minute. I want to deal with that last because that's going to be an important difference with SN2. So, but talk about the base first. And just like SN2, and you're stronger with two arms, SN2, you need a strong nucleophile. E2, we're going to need a strong base. And it turns out there's some subtle differences on who's a strong nucleophile, who's a strong base that we'll see a little bit down the road. But we do need a strong base. It's involved in the rate determining step, and the stronger the base, the faster the E2 elimination reaction. So your solvent here is a little bit tricky, and I'll kind of put this here. But it turns out this is not such a big deal here. I'll put polar aprotic there. And actually it will go faster in polar aprotic, and we just almost never do E2 eliminations in polar aprotic solvents. And the idea is that most of your strong bases are going to be like hydroxide or methoxide or ethoxide. And especially in the case of like methoxide and ethoxide, those are most easily formed by just dropping a little sodium metal in either methanol or ethanol. And so you almost always use methoxide and ethoxide in methanol or ethanol, which are protic solvents. And it actually is not a big deal for E2. It slows them down a little, but they work just fine. So I'm going to put polar aprotic here, and I'll put a little asterisk. It goes faster if it's polar aprotic, but they work just fine in polar protic solvents. So polar protic solvents are a much bigger deal for SN2 reactions than it is for E2 reactions. So faster in polar aprotic, work just fine in polar protic solvents. All right, we already talked about leaving groups, and so now I want to go back to the substrate here. So if you recall with SN2, we wanted the least substituted alkyl halide as possible. And that was because SN2 is all about backside attack, and the less steric hindrance, the better. Well, we're not doing backside attack here, and it has nothing to do with backside attack in an E2 reaction, so this requirement of our substrate goes out the window. And so it turns out the only thing really governing how fast an E2 reaction goes is how stable is the alkene we're forming. And since we know that more substituted alkenes are more stable, it turns out that the more substituted your alkyl halide, the faster an E2 reaction. Notice it also works for primaries. We're not forming a carbocation here at all. So primaries work pretty darn fast, just not as fast as tertiaries and secondaries. And notice you might be like, well, why aren't we doing the methyl, Chad? Well, to form a carbon-carbon double bond, you have to have at least 2 carbons. And a methyl halide only has 1, and you can't form a double bond with only 1 carbon. But outside of that, tertiary is fastest, then secondary, then primary for E2 reactions. We should talk about rearrangements here for a second. So E2 reactions, no rearrangements because no carbocation intermediate, whereas for E1, just like in SN1, rearrangements are possible. And then finally, stereochemistry. This is just a kind of put here because I want us to remember that for E2, there is this requirement that your hydrogen and your leaving group, your beta hydrogen and your leaving group, be antiperiplanar. And again, nothing to worry about as far as E1 is concerned in stereochemistry. Cool, so this is how we're going to distinguish between E1 and E2. And just like SN1 and SN2, the single biggest distinguishment is going to come at the level of base. Strong base is E2, weak base is E1. In fact, it's even a bigger deal than what we saw with substitution reactions, because at least with substitution reactions, SN1 and SN2, the substrate trends were the opposite, but now they're almost identical. The more substituted, the faster for both E2 and E1. And so your major difference really is going to come down to, do you have a strong base or do you have a weak base? That's pretty much it. So let's work a couple examples here. With SN1 and SN2, there was a lot more to worry about here, and we'll actually be able to kind of figure out what we need to know with just a couple of examples, so far fewer than we used for substitution. If we take a look, though, we'll approach this the same way we did with substitution reactions, and first thing, identify your substrate. So find your leaving group, and who's your leaving group of the first one? Well, it's bromine, and that is your substrate. Which means NaOH here is my base. And the solvent really isn't going to be all that important, which is why oftentimes we just don't even write the solvent. So this one's probably taking place in water. It might be being taken place in acetone or DMF, who knows? And really it's a non-factor for the most part in most E2 reactions. So in this case, I look at NaOH though, and I see that that is a strong base. And being a strong base, you're stronger with 2 arms. We're doing E2, not E1. And so in this case, if I look at my reactant here, there's my alpha carbon. It's a tertiary carbon, and that means that there must be 3 beta hydrogens, 2 that are secondary, 1 that is primary. And in this case, I'm not using a bulky base. I don't have a bad leaving group. We're just going to follow Mr. Zaitsev's rule, and he says, hey, use one of the secondary carbons. They have fewer hydrogens. They form more substituted alkenes. And in this case, they're equivalent, and so it doesn't really matter which one you choose. And again, whether I make the alkene on the upper left, the upper right or the lower right, it's the same thing either way. So it didn't matter which of these 2 adjacent beta carbons I chose. Cool, there's a product life is good. Cool, now I want us to predict the major elimination product for this next one. So, and again, find your leaving group. That's bromine, and that's your substrate then. Which means that methanol here must be the base. And again, just like with substitution reactions, a lot of students see OH, like, Chad, it's got an OH, it must be strong. And again, it's not like NaOH or KOH, which is a metal with OH. Those metal hydroxides are ionic, and you do have a negative oxygen in those cases. But this ain't that. We've got carbon bonded to oxygen. That's a covalent bond. There's no negative charge here whatsoever. Alcohols are weak bases. And having a weak base, we're doing E1 for a major elimination product, not E2. So when you're doing E1, I highly recommend first thing you do is just draw out the carbocation you're about to form. So if bromine up in leaves, we're going to form this sp2 hybridized carbocation right here. So, and in this case, the carbocation is not going to rearrange. It's tertiary and all the adjacent carbons are primary. So not going to rearrange. And in this case, all the adjacent carbons are therefore beta carbons. And they're all equivalent. So it actually doesn't matter which one we choose. So no matter how you slice it here, our product is going to look like so. And whether you draw the double bond here, here, or here, it's all the same thing. Cool. And again, that really tells us most of what we really need to know in distinguishing E1 versus E2. The only thing you might have to worry about in some other cases might be like a carbocation rearrangement, but we already kind of exposed ourselves to that with SN1 and stuff. So this is it. Much more interesting and much more detailed now. We'll find out that, we went and compared SN1 to SN2, and now we've compared E1 to E2. So in the next lesson, we're going to be comparing SN1, SN2, E1, and E2 all at the same time. And it's a little bit of a pain in the butt, and there's a learning curve. If you need some more practice with this or with comparing all of them, take a look at Chad's prep. And again, if you want to see all these videos that as they get released, go ahead and subscribe to the channel. But again, I won't be offended if you don't. So best wishes to you guys in the rest of your semester.